Welcome to the Centec Labcast. My name is Zhang Xulang. I'm a PhD student in the Sentinel team. Today, my presentation topic is granular syntax processing with multitask and curriculum learning. Syntactic processing includes foundational tasks such as parse-speech tagging, text chunking, and sentence boundary disambiguation. As demonstrated on the graph here, they are sequence labeling problems that deals with syntax from a fine-grained level to a cross-grained level. Parse-speech tagging looks at the function of each token, chunking looks at the structure of the phrases, and SBD looks at the construction of the whole sentence. Intuitively, we know that these tasks have strong linguistic correlations. In fact, traditional feature engineering methods commonly use parse-speech tag as input features for text chunking and SBD. However, in the era of deep learning, there are few recent research that investigate syntactic processing tasks through a linguistic lens. Therefore, we are motivated to explore whether combining syntactic tasks of different granularities can have a complementary effect on the model's understanding of syntax. So to achieve this, we propose to study the extent to which they complement each other in a pairwise multitask learning setting. The reason we choose to use multitask learning is that it takes advantage of sharing parameters and learning features from multiple tasks, which makes it the most common way to integrate complementary tasks for better performance. Specifically, we choose soft parameter sharing MTL because hard parameter sharing shares the hidden layer between all tasks, so they share the same representation space, which makes it less adept at capturing task-specific information. But soft parameter sharing keeps a separate model for each task and utilize constraint mechanism to share information between tasks. So it is more flexible for task-specific representation. Therefore, we choose the latter approach. Furthermore, we also address the non-parallel label learning issue in MTL. So this happens when the dataset used to train one task is not annotated with the other task labels, which can lead to the model biasing towards a specific task. There are limited research on how to resolve this issue while also mitigating the resulting bias. So we employ a curriculum learning mechanism to address this issue. Curriculum learning in general is defined as an approach to automatically select the most suitable samples for each training step. Here we are proposing a CL mechanism that selects complementary sample to mitigate task bias. We hypothesize that with the right combination of input data from non-parallel datasets, MTL models can achieve better performance and smoother convergence. So the figures here shows the MTL model architecture. It consists of two task towers, and in each task towers, we employ a LGDS layer after each encoder layer to share information between towers. And as shown in the figure here, the LGDS employs CNN and bi-affine attention to incorporate local and global dependencies that are learned from both tasks. For instance, a LGDS layer in task C tower would take in the output of the previous block from the task P tower and use CNN to extract task P information within the local context of each focal token. And we capture the long-range dependency from task P to task C by computing bi-affine attention matrix using task P representation from the previous block, and also task C representation of the current block. So using this bi-affine attention matrix, we can get the task P information enhanced by the its global task C dependent information. So finally, we add the local and global task P representation together and concatenate it with the current task C representation to inject relevant task P information into the task C tower. And after a few blocks of this, we can then use a CRF layer to make predictions. Next, I'll introduce our CL mechanism. As I've mentioned before, we employ the CL mechanism to target the non-parallel label data issue. As you can see on the table below, although the chunking dataset Cornell 2000 is annotated with parse speech label, chunk labels, and sentence boundary labels, the parse speech tagging dataset WSJ does not have chunk labels. And the SBD dataset is only annotated with sentence boundary labels. This will cause the model to bias towards one task when we jointly train it on both task datasets, especially when the differences between the volume of these datasets are quite large. So the core concept of our CL mechanism is that when training on a non-parallel label dataset, we select the most similar sample from a parallel label one. We hypothesize that the feature alignment of multiple task inputs can help the neural networks learn features from similar spaces. In contrast, features from very different spaces may lead to unstable learning. For experiment, we first compare the performance of our model on each pairwise MTL combination with single task learning and multitask learning baselines. The top panels shows the single task learning baselines, and the second panels show the MTL learning baseline, both on their own and with our CL mechanism. We show the results on two variations of our models, one using LSTM layers as encoder, and the other uses transformer layer. From the table, we can see that both SBD and chunking achieves the best performance when jointly learned with parse speech tagging. Notably, when paired with parse speech tagging, our method outperforms the text chunking SOTA. We can also observe that parse speech tagging achieves better performance when jointly learned with SBD than with chunking. But in general, it receives limited benefit from MTL with more coarse-grained tasks. Lastly, by comparing MTL baselines with and without CL, we can see that our CL mechanism consistently brings significant input to the MTL models. Next, we conduct an ablation study on the best performing pairwise MTL combination. By comparing without MTL and without LGDS, we can see that the joint training between syntactic tasks can provide useful features for each other. And by comparing without the LGDS without CL, we can validate the effectiveness of our soft parameter sharing mechanism. By comparing fine-tune and without CL, especially for SBD and parse speech tagging, we can conclude that fine-tuning cannot achieve stable learning for MTL. Also, there is a sharp drop on the SBD performance when only using the WSJ dataset for joint training. As a result, the parse speech tagging performance also suffers. And the same reason is responsible for the performance degradation of chunking with parse speech when it's solely using the Cornell 2000 training set for the multitask learning of chunking and parse speech tagging. Lastly, the comparison between without CL and our transformers further proves the effectiveness of our CL mechanism. In this part, we first analyze the trade-off between time cost and performance using text chunking and parse speech tagging as a case study. So CL1 here means that we randomly sample the equal number of instances from both task datasets in a batch. CL2 means that for each WSJ instance, we sample two Cornell 2000 instances and select the most similar one from these two instances. The same goes for CL4 and CL8. We can see that the average accuracy increases as we sample more candidate instance, but the time cost also increases. We conclude that CL4 achieves a good balance for the trade-off. Next, we analyze the loss curves of CL1 and CL4 for each pairwise MTL combination. And in each figure, the figure A is given by CL4 and figure B is given by CL1. We can see that for all combinations, the fluctuation of the loss curves in figure A is less than those in figure B's. This shows that our CL mechanism is effective in selecting complementary examples to optimize and stabilize the learning of both tasks. So to conclude, we propose a MTL framework with a novel soft parameter sharing mechanism. And we also propose a CL mechanism to improve the ability of the loss convergence for the non-parallel label data in MTL. And we also study how syntactic tasks with different granularity complement each other through pairwise MTL. Thank you for listening.